Hello everybody, welcome to Blue Marble Science. How stupid can you be is not a challenge, but some people seem to take it as one. Tell you what, let's let Mitchell from Australia have a go at it. Mitchell, you're up. Warning, severe facial and monitor damage alert is in effect. Get out those oven mitts, push the monitors back out of punching range, and let's light a dumpster fire and have some fun. Mitchell from Australia was trying to do a debunk of something WheresWally did, and clearly Mitchell doesn't understand the trigonometry, so I thought I would try to help him out a little.
Oh, hi, Blue Marble Science. How are you, mate?
Oh, hello, Wally.
Oh, yeah, Mitchell. He's being a right proper galah, isn't he? Yeah, go on, rip into him. Let him know all about trig.
Yeah, well, let's see if we can do that.
So this was a screenshot I was going to use this morning of this bloke I was about to debunk, and look at the problem it creates. So he's measuring something like a satellite here. He thinks he's got geostationary satellites, and look at the right angle that he's created. Where's the tip of the right angle? That's meant to be the height from the Earth, which is meant to be over here somewhere. He's put the edge of the right angle over here because he's measuring from this location. So he's thinking he's getting an angle from this location here on the edge of the Earth. He's measuring an angle to what he calls the geostationary satellite. And where's the geostationary satellite's GP point? A couple of 100 miles beneath the Earth, a couple of 100 kilometers beneath the Earth.
No, Mitchell, the GP is at the surface of the Earth, not a couple of 100 miles below the surface of the Earth.
This is the problem that it causes for the globers. Us flat earthers, we have no problems. We can sit back, places like this, watch the sun come up, look at the beautiful palm trees, just chill, you know? Just detail how beautiful our flat earth school is. But for the globers, this is the kind of mental torture that they have to put themselves through. Yeah, so this right angle here is meant to be on the surface of their globe, if they think it's a globe. Why is it running in under a couple of 100 miles beneath the surface of their spherical globe? Because that right angle, because they know they have to have a right angle.
No, you don't have to have a right angle, Mitchell, and I'll show you why in a minute.
You need to be able to measure something.
Oh, Bev, be quiet.
To measure an angle, yeah. So it's going through. It's going through their Earth. It's forming a chord because he's trying to make an angle here. He reckons he's measured 31.95 degrees here on the surface of his globe.
No, he reckons he's in Perth, Australia, at a latitude of 31.95 degrees south. Is any of this ringing a bell?
Irish Dublin girl says, "Show me your perfect flat Earth model." Oh wait, you guys don't have one? Absolutely. Why would we need a model? Because all the maps that we use for navigation, for the layout of the land, they're all flat. As I said in the start of the show, all the maps that you use for navigation, for layout of land, for reality, yeah, the aerial photography, the things that have been measured physically by theodolites, by surveyors, they're all measured flat.
That's incorrect, Mitchell. Certainly, we use flat maps over short distances, and it's not a big deal. This is a Delta airline route map out of Salt Lake City to U.S. destinations primarily. Try to find a straight line on that map. Why are those lines all curved, Mitchell? And I'll tell you why. It's because when we flight plan, we don't use that flat map. Flight planning is done using great circle routes. That's what those arcs are for. It's not because the guy didn't have a straight edge he could use. It's because that's the actual shortest distance between 2 points, because the surface of the Earth is not flat.
Because you have to treat everything as flat in the first instance to get angles. If you're on a globe and you're trying to get angles, this is the kind of mental torture you're putting yourself through. That right angle there, you need a right angle to the GP of something like a geostationary satellite. Why is the right angle not going to here? Because it's going to be shooting off into space here.
Level is horizontal.
Level is not horizontal, Biff. Stop saying that.
You can't achieve a right angle on a curved surface. Yeah, and you can't just have the curved surface as the baseline of your triangle. Has anyone ever seen a triangle with a curved baseline? It just does not work. These are the problems that the globe find themselves in. Yeah, not a problem on a flat Earth. We're just sitting back here, watching the palm trees, watching the sun come up. No problems on flat Earth.
Actually, you've got huge problems on a flat Earth, like navigation trying to use a sextant, but we'll get to that in a minute. First, let's deal with this. This is what we call a scalene obtuse triangle. It's a triangle where none of the sides are equal length and none of the angles are 90 degrees. And this one is obtuse because one of the angles is clearly greater than 90 degrees. Now we can always take one of these triangles and make two right triangles out of it, just as I show there, but that's not the only way to solve the problem. What if we know this? What if we know all the angles and the length of one of the sides? Well, let's identify some points. First of all, that's the location of the satellite. That is the center of the Earth, and that is a position on the surface of the Earth, in this case, Perth, Australia. We know the declination from the satellite to Perth is 5.05 degrees. We know the latitude of Perth, and that's 31.95 degrees. And those two sum to 37 degrees, meaning that the third angle has to be 143 degrees. Are you with me so far?
Are we understanding each other?
We know one other thing. We know the radius of the Earth. The radius is 6,357 kilometers. And that's not a supposition. That is knowledge we've had for more than 2,000 years fairly accurately, and very accurately for hundreds of years now. Now this is what we call the law of sines. And it says the ratio of the length of one side of a triangle to the sine of the angle that's opposite that side has to be constant. So A divided by sine A equals B divided by sine B, and C divided by sine C. So let's give these things some labels. We'll call that side A, we'll call that side B, and we'll call that side C. The angle opposite A is 5.05 degrees, so that's angle A. The angle opposite side B is 31.95 degrees. We'll call that little b. And the angle opposite side C is 143 degrees, so we'll call that little c. Now, the other thing we know is the radius of the Earth, 6,357 kilometers. So, 6,357 kilometers divided by the sine of 5.05 is 72,218. That number has to be constant for all three sides. So B is the sine of 31.95 degrees times 72,218, and that's 38,216 kilometers. Let's stick that in. Side C is equal to the sine of 143 degrees times 72,218, and that's 43,461 kilometers. Let's put that in. What do you know? Now we know the length of all three of the sides, and we know all three of the angles.
That was nice, that, wasn't it?
Yeah, that is pretty neat. Thanks, Biff. But that's not what we're looking for. We're looking for the altitude of the satellite. So first let's draw an arc, and that's the surface of the Earth that's being represented. Now let's put some dots in here. There's the center of the Earth. There's the satellite. And we know the distance between the satellite and the center of the Earth is 43,461 kilometers. But that's not what we're looking for. We're looking for the distance to the surface of the Earth. Well, that's pretty simple. We know the radius of the Earth is 6,357 kilometers. Therefore, all we have to do is subtract that from 43,461 kilometers, and the altitude of the satellite above the surface at the equator is 37,104 kilometers.
That was nice, that, wasn't it?
You're right, Bev. That is nice. And, of course, that's exactly what Wally got. So you see, no right angles are needed. All you need to know is a little bit of trigonometry.
The question was, what distance can the sextant cover? So if you've got an angle to a star of 15 degrees above the horizon, then as we know, for every 1 degree below 90 from the GP point of the star is 69 miles. So we can extrapolate that out. If we're measuring 15 degrees, that means there's 75 degrees from the 90. So 69 times 75, and that's something like something like 5,000, over 5,000 miles to the GP of that star if we're shooting it at 15 degrees above the horizon. Over 5,000 miles. And that creates an area of equal altitude of 10,375 miles. Yeah, so here, I've actually got the picture here. Look, if we're 15 degrees, sorry, if we're on the horizon, okay, so that's someone on the horizon, and they're shooting Polaris. Did I say somewhere on the horizon? I meant the equator. So if you're 15 degrees above the equator, okay, and you're looking at Polaris, which is meant to be the geographical north, okay, so you're measuring, if you're measuring 15 degrees to Polaris, then that means the GP to Polaris is about 5,000, it's half this number. This is the diameter. Yeah, so you're creating an area of equal altitude of 10,375 miles. That's just one observation. And obviously, because you've got a right angle triangle here, this angle here, 90 degrees to where Polaris comes down to is the GP point, the geographical position, the place on. So it's measuring 5,000 miles horizon. Absolutely. Absolutely. That's what we extrapolate out from using the sextant. Yeah, so if you're here, 15 degrees above the equator, and you see Polaris, 15 degrees above the horizon, that's an angle of 15 degrees. Okay? Obviously, it's not to scale, but I'm just, because this map is very distorted, because it's been wrapped on a globe and then put on a flat surface. Yeah? That's what most maps have. They're very distorted because of that fact. But if you're measuring 15 degrees to Polaris, you can extrapolate out that the GP is a straight line from your observer point, yeah, to that GP. Straight line. 5,000 miles if you're measuring 15 degrees to Polaris.
So now we have a problem, Mitchell. We've got Polaris over a GP, which is what we call the North Pole. And you have told us, and we agree, that each degree of latitude is equal to 60 nautical miles. Well, if we're in the northern end of Greenland at a latitude of 75 degrees north, that's 15 degrees from the GP. And 15 degrees times 60 nautical miles is 900 nautical miles. That fixes the altitude of Polaris at 3,360 nautical miles above the GP. Okay. What happens if we go to a southern latitude, let's say 15 degrees north? Now that's 75 degrees from the GP, and 75 times 60 is 4,500 nautical miles, and that fixes the altitude of Polaris at a mere 1,210 nautical miles. How can that be, Mitchell?
That was nice, that, wasn't it?
How can Wally be in the Caribbean at 15 degrees north latitude, looking at a Polaris which is 1,210 nautical miles above the GP, and then travel to 75 degrees north latitude in northern Greenland and see it 3,360 nautical miles above the GP? So I've got a couple of questions for you. Number one, can you see Polaris from Australia? Of course you can't. Tell me why not. And number two, what is the correct altitude for Polaris? It can't be in two places, or for that matter, an infinite number of places at the same time. So what is the correct altitude, and how do you ever make this work on a flat Earth? If you come up with answers for either one of those questions, get back with us. In the meantime, hey, thanks for watching. I hope you guys enjoyed it. Don't forget to hit the like and subscribe buttons down there. Tickle the little bell if you want notifications. Shout out to the patrons and PayPals. I appreciate everything you guys do. And we'll see you on the next one.